Hey everyone, welcome back to the HS Tech Channel.
There we go. Get the vocal processor going. Hopefully this will hold your attention as we discuss VPNs for dummies here on the HS Tech Channel. Death by PowerPoint, but also Death by VPN special. We're going to look at how VPNs were done in the olden days, how they're done now, and how we can learn from what was once the standard as we progress through building our VPNs. We are going to start just with a quick and brief introduction to what we're actually going to go over. As I mentioned, we're doing some historical analysis, but also some modern analysis. We're going to talk about how remote access connections were done back in the day with SLIP and PPP, and we're going to look also at some other forms of PPP connections, and of course we're going to talk about what SLIP and PPP actually are, and we're going to look at these PPP over IP methods, which, while these may seem foreign to you now, by the end of this video you will understand are the fundamental backbone of the enterprise VPN network configuration techniques that we use today. However, before we begin though, we should probably review our network stack layers. This is a diagram, although you'll see things a lot similar to this in pretty much every networking textbook and PowerPoint slide deck and CompTIA training course that you'll ever encounter in your life. This is a rather questionable, but we're going to roll with it, mock-up of how data is encapsulated when you transmit it on a network. So let's say we have our application payload and we want to transmit it inside of a TCP session, so in a sense a pipe that's just dedicated for us. That's what happens when you open a TCP connection. It gives you your own private pipe, so to speak, although it's not very private. It just means you don't have to process everybody else's packets. Those are obviously being carried over IPv4, but you need something that can carry those IPv4 packets, so our network uses Ethernet, and we're using both the Ethernet Layer 2 protocol and the Ethernet Layer 1 protocol. So this is like regular twisted pair Ethernet. And we're going to see how much of this we need to encapsulate in order to form a VPN. And more importantly, is that a good way of doing things, and when do you know when to use certain kinds of VPNs? Like, if you encapsulate just this network layer and above, you're not going to be able to capture other packets on the data link layer that aren't of the TCP/IP protocol family. But if you encapsulate here at the data link protocol, you can encapsulate pretty much anything. And so we're going to take a look at that and how other data link protocols are able to carry those. So in a sense, we're going to try to build tunnels that will encapsulate either that network layer or either that link layer, or possibly both, depending on what the mode is. However, we need to also discuss how tunnels will replicate, in a sense, the physical layer. So we're going to start with some network layer tunnels, so in other words, tunnels that can only carry IP datagrams, and then we're going to also look at some tunnels that function as link layer tunnels a little bit later here in this episode. So let's start with the original one. This was called SLIP for Serial Line IP. This was used quite extensively in the early days of the internet, but nowadays has fell out of style quite drastically for its relatively poor performance and certain design flaws. But serial line IP allows you to create a TCP/IP network connection between two hosts, usually Unix machines, over a serial cable rather than an expensive Ethernet cable. Ethernet cables in the era when SLIP was very common consisted of coaxial connections, not the twisted pair that I'm sure you probably know of today. These coaxial Ethernet networks were great, they were cheap, but unfortunately they didn't go very far, and also SLIP in a sense kind of predated when Ethernet was really commonly used. So this was great for the time, however it was hideously simple. You had to manually configure it, you had to manually set the address and everything. There was no security mechanisms whatsoever, so if you caught up a remote machine and initiated a SLIP connection, by the time you initiated that SLIP connection it was presumed that you were already an authorized user. But this was very common back in the day, as you might would expect, but this is still used in embedded systems because of how simple it is really to implement. PPP was the logical successor to SLIP. This is a point-to-point protocol, as we say, and this is an actual real link layer protocol. SLIP can only carry IPv4. PPP, though, IPv4, IPv6, Novell IPX, Digital Equipment Corporation's DECnet, Apple's AppleTalk, NetBIOS frames, and also the OSI networking model. Now, not to be confused with the OSI stack, but there is a network protocol family known as the OSI or the ISO protocols that competed against TCP/IP. Nowadays it's completely almost entirely extinct, but it was a thing at one point. PPP also offers you a variety of very handsome features that would certainly be helpful on slow links, such as compression. It also provides you with encryption. However, the Microsoft point-to-point encryption, MPPE, as it's known, is very insecure and is not exactly something you should trust. You would want to use a real security mechanism like IPsec, which we'll talk about as well. This also provides real authentication mechanisms, so rather than just hoping and praying that whoever ran the SLAttach command, which we will look at, is already authorized, PPP actually allows you to do some real username and password checking. PAP is the PPP authentication protocol, or the password authentication protocol as it's actually known. It's just a plain text password. CHAP is a challenge handshake authentication protocol. It's a little bit better because it requires an actual challenge be sent to and from the client. However, it's still not that good. MS Chat v2 was a step up above chat, but nowadays you can crack it in an extremely fast amount of time. PPP also has an amazingly useful feature known as multi-link PPP, or MLP. Not to be confused with, I believe there's a TV show that also has those initials. Multi-link PPP was great back in the days of when everything was slower. So you had dial-up modems, and you had 56 and 64K CSU-DSU interfaces. You had T1 interfaces and E1 interfaces, which were just multiple bonded CSU-DSU 56 or 64K lines. And this really provided you a way to attempt to multiply your link speed with relative ease. Maybe you leased out 4 T1 lines. Great, that meant 1.536 times 4 megabits could be yours. And because of the way that it did traffic scheduling, it was extremely easy to implement. And as such, pretty much every major PPP implementation out on the market supports the MLP protocol. So the VPN dialer on Windows, as well as the dial-up dialer, which is the same code base, those all support MLP. PPPD on Unix, one of the most replicated versions of PPP, supports it. The OpenBSD one, as well as interfaces on Cisco iOS that are configured to use PPP encapsulation, they support it as well. HDLC, while we're not going to really talk about it much, is a serial WAN protocol, just like SLIP and PPP were, except it was a little bit more of a general way of doing things. So you may have configured a Cisco router before and used encapsulation HDLC on a serial interface. That is actually Cisco's specific version of HDLC, but HDLC was used as a building block in a way for various other serial protocols. So LAPF, Link Access Protocol for Frame Relay, you've probably heard of Frame Relay, it's very similar to HDLC. LAPB is what X25 used. LAPM, Link Access Procedure for Modems, is what some high-speed dial-up modems used. And then, of course, LAPD is what ISDN used, for anyone that actually has used ISDN. So how can we carry those protocols? Well, we can use a standard RS-232 serial cable, which includes a dial-up interface. We can use something called V35, which is a high-speed synchronous serial interface. We can use T1 or E1 controllers, as well as a fractional version of T1 and E1, which some folks know as 56 or 64K CSU DSUs. So a T1 controller, for example, is 24 bonded 64K or 56K CSUs or DSUs. But we can also carry this as a payload over another network stack. So how might we do that? Well, in a way, we kind of got to go from a link layer emulation or network layer emulation to a VPN. So because of how we've established our OSI layers way back all the way over here on this diagram here, if we are coming up with a data link protocol, so both PPP and HDLC can kind of be seen as data link protocols, SLIP not so much, because if you examine SLIP frames, they are exclusively just IP datagrams. That's it. There's not really any protocol field. So in a way, we need to figure out a way to adapt these quasi-link layer protocols into something we can carry over the internet, which of course speaks TCP/IP, unless you're watching this from an alternate timeline where TCP/IP failed at winning the protocol wars. So we can just take our standard serial port data stream, that's just an ASCII byte stream, and we can send that straight over the network protocol of our choosing. You can send it over TCP, which you should not do. You can send it over UDP, which is very commonly done, or you can send it over raw IP datagrams, or you can send it over raw Ethernet datagrams. Do note, however, there's a fundamental limit in the amount of encapsulation that you can employ. If you have a standard Ethernet network that has a maximum transmission unit of 1500 bytes, the more encapsulation means the more space you're wasting in each packet. So you do have to watch out for that. You need to choose the leanest mean of encapsulation that will achieve the results that you want. So what are some examples of ways that PPP, for example, can be encapsulated? Well, the most common one, you may have heard of it, is PPPoE. This is point-to-point over Ethernet. And initially, way back in the day, about 20 years ago, this is really commonly used by DSL ISPs, because a DSL modem might be configured to take some PPPoE, ATM, asynchronous transfer mode, being the native protocol of the DSL networks, and just take a ATM PPP session, just re-encapsulate that into Ethernet, such that normal PCs with cheap Ethernet controllers can talk on a DSL network. This was relatively good in terms of a performance overhead standpoint. It's relatively high throughput, relatively simple to manage, but nowadays this is actually, for some reason, used on a lot of PON and GPON networks, specifically apparently over in Asia. Apparently this is somewhat commonly used in Japan. It's pretty fun to play around with, but you have to be a diehard network engineer to actually legitimately want to set this up and use it. PPP over ATM, as I mentioned before, ATM is a radically different network topology compared to Ethernet. This is it's a virtual circuit oriented protocol. It was kind of made by a bunch of telephone engineers, and it really shows. PPPoE was formerly found on DSL networks, and some DSL modems as well as DSL interface cards exposed an ATM interface directly. So you would need to have an operating system or some kind of protocol stack that understood ATM, and then you could establish an ATM virtual circuit connection, and you would run PPP inside of that. The alternative to this was something called CLIP, which is classical IP over ATM, and then the other option was LAN, which was LAN emulation. We're not going to talk about either one of those. Those are their own hideously complex thing unto themselves, but just know that those are out there. There are other forms of tunnels that we can do that are higher up in the network protocol stack. So, for example, a logical successor to SLIP, if you wanted to, quote, encapsulate SLIP over IP, well, because SLIP only carries IP datagrams, if you take that data stream before you send it into the function that sends it out on the serial line by wrapping it up into a SLIP physical layer protocol, into a SLIP data link protocol, an IP-IP tunnel is a relatively simple analogy to how that would work. And don't worry, we're going to look at all of these and what they look like on Wireshark, because I think that a video is worth 1,000 words. You may have used a 6-in-4 tunnel, sometimes called a SIT tunnel, a simple internet transition tunnel. Guess what? Same thing as IP-IP, except rather than carrying IPv4, it carries IPv6. GRE, generic routing encapsulation. This is a protocol that's actually somewhat similar to PPP in the sense that it actually has a protocol field. So it says, okay, this is a GRE packet, this is carrying whatever. This is carrying IPv4, IPv6, DECnet, IPX, AppleTalk, NetBIOS, Frames, OSI, who cares? It actually kind of is its own link layer protocol. And I'm sure you could probably take the contents of a GRE packet, send that over a serial line, and come up with a relatively questionable quality link layer protocol. But we will examine all of these here. There are other things we're not going to cover, such as VXLAN, the Virtual Extensible LAN. This is a way of re-encapsulating Ethernet frames into UDP. These are generally implemented in kernel mode networking stacks and generally tend to be extremely performant. MPLS, multi-protocol label switching, this was the ATM killer. MPLS is its whole convoluted topic on its own. We will not be covering that in this video. I might consider covering it in the future if people truly want to know about it, but we're not going to talk about it. OpenVPN has been done to death. It is a user-land tunnel and tap VPN, which means its performance can kind of be somewhat questionable, and it uses a variety of common crypto systems such as RSA for doing its encryption and decryption. WireGuard is a user-land tunnel VPN, though recent times it has become a kernel mode VPN, and it is an IP and IPv6 only VPN solution, well, for the most part, and it uses a encryption standard known as CHA-CHA-20, which is intended to be fast on CPUs. However, we need to actually talk about how all of this is done. So how do we recreate that logical physical layer? Well, here is an example of a PPPoE packet. as it was a straight raw Ethernet frame. So this right here shows the actual Ethernet frame itself. So you've got the preamble, you have the source and destination MAC address, you have the ether type, which will identify this as a PPPoE frame, then we have the payload, then we have the frame check sequence. Inside of the payload, it's going to have a PPPoE session header. So a type, a code, and a session ID, then a length, then the actual real PPP payload, and then this right here, this protocol and information, this here is the actual PPP session. And the only thing that really survived from the cut from the serial line when we adapted PPP to run over Ethernet is we only care about the protocol and then the information, or the actual downstream protocol. So if we extended this diagram out, you would have, for example, protocol would be 0800, which of course is hexadecimal for the ether type value that represents IPv4. Do note that this protocol number and this ether type number, these share the same numeric address space, I believe. So if you know your ether types, you know your PPP protocol numbers. And then the information is, as I said, the payload, and then you would see the downstream protocol in there. Okay, so that's great and all, but as you probably know, the internet may not necessarily be built on Ethernet. There may be virtual machines that are being used as routers on the internet, and those may not necessarily have a full layer 2 Ethernet interface attachment. They may only have a tunnel interface that can only carry IPv4 and IPv6 packets. The solution for that was to invent something called PPTP. Now this is a very old means of setting up a PPP over the internet session, and it used port 1723 on TCP to establish a session, and then after it established a session, it would use GRE to actually carry the payload. So you would have your IP header, you'd have your GRE header, you'd have your control byte, and then you'd have your information of the GRE header, and that of course contain right here the PPP session. L2TP was the successor, in a sense, to PPTP. This, rather than establishing a GRE tunnel and having a convoluted difficulty of being able to route that, used UDP instead of GRE. And in a way, this actually kind of resulted in smaller encapsulation. And it was much easier to configure IPsec for, because rather than having to have two IPsec policies for that port 1723 session initiation thing, then that GRE session transport thing, now you only need one for the just the direct L2TP session itself. And that usually flows over UDP port 1701. And we'll look at how this functions, and oftentimes these are encrypted using IPsec, which we'll get to in a moment. IPsec. Okay, this is a simple, relatively simplified diagram of various forms of IPsec encapsulation. This is not to be taken as 100% accurate. I believe some of these numbers are wrong, so don't pay super close attention to the sizes and bytes of each one of these frames. So if we have just our plain unencrypted TCP/IP, note that this diagram operates at the IP network layer. We don't know what these packets are going over. They could be going over Ethernet, they could be going over PPP, they could be going over SLIP, HDLC, it could be going over anything. We don't know. It's an unknown, and it doesn't matter. So we're going to carry our payload here inside of a TCP packet, or inside of a TCP session over IP packets. This right here, this is unencrypted. Maybe we want to authenticate ourselves to a remote system. Well, for that, we can use the authentication header scheme. And this provides, in a sense, a simple but not necessarily encrypting the rest of the payload. And there are two ways that this can run. Now, obviously, with the so-called AH mode of IPsec, you absolutely can encrypt the rest of the payload, as you oftentimes would do, but IPsec has two modes of operation: transport mode and tunnel mode. With transport mode, you're operating at the transport layer, which is kind of strange to think about, but if we go all the way back over here, we're operating at the transport layer, which means at this dividing line between the cyan and green, or for my colorblind viewers, the network and transport layers, right between there, they're at layer 3.5. Oh great, here we go with the decimal layers. Ugh. That's why the OSI stack can be very questionable when we start talking about VPNs, but they're at the gap between the network and the transport layers, that's where we'll insert our, I guess you could say, where we start to pay attention, where we're starting to encapsulate our data. So we will insert the authentication header between the IP header and the TCP header, and then from there, everything down there is either authorized or at some point we'll get to encrypted. Tunnel mode is handy if you're making a router that connects two sites via an IPsec tunnel, and you can essentially configure your IPsec stack to do its own form of built-in tunnel. This does not really require anything, but this is kind of an IP tunnel. Is really what this is. This is fundamentally, it's just a protocol for IP inside IP tunnel. And you will just take your second IP header, this would be sort of the inside network, and then you would then have this secured for the outside network being the internet. However, AH is very rare. Oftentimes you're going to see ESP, encapsulating security payload. This is the real deal. If you go sniff packets on the internet, this is probably what you'll see. But there's two ways that ESP can be done. There's straight ESP here, where we are essentially replacing TCP as the dominant protocol inside the IP packet. Then there's a UDP encapsulation of IPsec ESP datagrams. This is something we'll talk about in a second here. But this has the exact same facilities as the authentication header scheme. So you have your transport mode, which only secures the session for you, and then tunnel mode, which you may use for a site-to-site configuration. However, if you're running a downstream tunnel protocol, like you're establishing a form of PPP session inside of this, there's no reason whatsoever to use tunnel mode unless you, for some reason, want to slow down your network performance. If you're behind NAT routers, now I need to make it clear, the word NAT, or I guess the acronym NAT, has different definitions depending on who you ask. This is something I found out and was quite surprised to hear. I asked 10 network engineers what NAT meant, and I heard 3 different answers. When I say NAT, I'm referring to what the Cisco iOS people are going to call NAT overload, what the classical TCP/IP stack standardization people will call port address translation, or PAT, and what the OpenBSD and FreeBSD guys are going to call NAT. Okay, so in other words, this is the thing where you have basically many to one NAT, or I'm sorry, going out it would be many to one going out and then one to many going in. And this is where you'd have your port forwards and all the stuff we expect on like a home router. This is what I mean by NAT traversal, is this is to fit through home routers. So you would just port forward UDP 4500, and also you need to port forward UDP 500 for ISACAMP, which is used to establish an IPsec session. And once you've forwarded 4500 and 500, you're good to go. However, you should also forward whatever ports are required for the downstream tunnel protocol, which we will examine. So with that being said, it's time to go ahead and roll into the live demonstration portion of this video lecture. We're going to examine all of those protocols by looking at a bunch of pre-cooked samples that I have collected, as well as doing some live demonstration of some of the more serial-oriented protocols. So we're going to do that in reverse order. We're going to start with the serial-oriented protocols, then we will go to the more advanced ones. Okay, we're going to go ahead and begin with some live demonstrations. We will be using a variety of virtual machines for these demonstrations, all of which have been configured to have virtual serial ports that are connected at each other. So if I open the settings dialog for this virtual machine here, it may be a bit difficult to see because it is grayed out and this font size is rather small. This right here will be piping its COM1 serial port into a Windows named pipe, and so will port 2. Port 1 is connected to this OpenBSD virtual machine, port 2 is connected to this DOS virtual machine, and we will be demonstrating what it takes to set up various connections between them. So we will start with SLIP. SLIP is by far the easiest of pretty much any serial line networking solution to get going. It is probably the easiest to write a driver for, and for all intents and purposes, it's a good place to start. So we have 2 serial devices on this system. Well, we actually have 4, but only 2 will be functioning in this demonstration. We have TTYS0 and TTYS1, and of course that corresponds to COM1 and COM2 respectively on your motherboard's serial port controller if you're doing this on a real machine. And these 2 machines being connected via a pipe will be equivalent to a null modem cable. However, this is a 3-wire null modem cable. This is not a full null modem cable, so we only have transmit, receive, and ground. So we will need to take considerations in for that, and you will need to as well if you are using an actual null modem cable. So we will establish a SLIP connection between Linux and DOS. Now, this is no Linux in particular. This is just kind of a generic system I made. It's not really anything. It's not branded anything, it's just something I kind of clobbered together myself. So this has a bunch of helpful networking utilities, and one of those that you will need is called SLAttach, okay? So this is a program that has been vanishing from modern day BSD, Solaris, and other such operating systems, but it is the command that you use to configure a SLIP session. Note, if you're on an old version of like System 5 Unix or an old version of BSD, the SLAttach command has different syntax from what it is in Linux. Do be mindful of that. But this is not too terribly hard to do. We need to do SLAttach-L for local, which means you have another computer connected locally, in other words, hooked up via null modem cable. We want to do the SLIP protocol, as opposed to CSLIP, which does header compression, which will certainly help out for slow links. Speed will be 9600 baud, and in our TTYS1, now you need to put an ampersand at the end of this, or you need to do the Control-Z and then BG trick, because otherwise it will eat your terminal. Now, if we do ifconfig SL0, you can see it's there, but it's an unconfigured interface. A note about MTUs in the world of SLIP. The default MTU in a lot of cases is either 296 or 1006. There is no set MTU for SLIP. I use 1006 because it's pretty good, and for the most part you're not going to run into trouble. But we do have to sit here and manually configure this interface with an IP address. Remember how I said that there is no automatic configuration. You can use DHCP on SLIP, but why in the world would you do that when you can just do ifconfig SL0 198.18.20.1, and because this is a tunnel link, we need to say destatter 198.18.20.2 MTU 1006 up. We'll come over here. Now, we're not using a traditional DOS TCP IP stack. We're going to use something called the K9Q Network Operating System. It's really for amateur radio packet work, but it provides this really nice and containerized environment here, and so these are just the commands that it will run at the start. We only care about this one here. So attach an asynchronous device at port 3F8, interrupt 4, in other words COM1, SLIP protocol. Our interface name is going to be SL0, 1024 buffers, yada yada yada, 9600 baud, okay? So remember the destatter that we plugged in? Here's the destatter. Now, this doesn't really have a concept of a destatter because it's just kind of done based on the network address and the subnet mask, so in a way you don't really need it. So we will go ahead and exit, and we will run net, and then it ran all those startup commands. So if we do ifconfig SL0, you'll see that we have this appropriately configured. Now, NOS has a very interesting way of pinging. If I attempt a ping, hopefully this will work on the first try. If not, oh well. There you go. So if I ping an invalid address, 198.18.20.25, it'll never come back. It will just wait indefinitely. Now, this can be a problem because we sit and constantly do pings, and all of a sudden they come on all at once. Your terminal can scroll out of the way, but that's a problem for users of this program, not people learning how to do networks. But you can see that there was packet transmission that occurred, and you can see that another packet was sent. This packet did get sent on the link because it fits the net mask and the network address and the host address parameters, so as far as it's concerned, it's good to send that down the link. Now, if we come over here to Linux, you will be able to see that it is basically doing the same thing, and the network, or I'm sorry, the net mask on here is a stroke 32 net mask, So if I ping some other garbage address, 108.18.20.123, it's going to send them actually out the Ethernet interface, because that's where the default route is. But at this point, we have a SLIP interface, and it works reasonably well. But this is also very primitive. This isn't very good. The bandwidth, when you transmit certain packets, will go through the roof, the bandwidth utilization, due to how SLIP handles escape sequences within packets, because that's the thing you need to do in order to mark the end of the packet. Essentially what SLIP does is all packets end with the hex byte C0. If for whatever reason you encounter a C0 in the packet, you must convert it into a double byte escape sequence. So if you have a packet that has a lot of C0s, which is unlikely to ever happen, mind you, but if it does, your SLIP connection will grind to a crawl as you are effectively halving your throughput. But with that being said, we're going to go ahead and pkill-9%1. Actually, I'm going to show you why I'm doing that, because that's our first job. Sometimes it takes a couple kills. There we go, and then we're going to shut down this DOS virtual machine to free up that serial port, because we're going to run something a little bit different here soon. Now, we're going to get into PPP. These two machines are connected on their respective COM1 ports, so of course on OpenBSD we'll have that available to us, and on Linux it's good to go. Now we're going to explore something way more difficult. PPP is, for new users, a bit of a nightmare, but I'm going to make it easy. PPP, being a relatively simple protocol, is not too horrendously difficult, I would say. However, there are two major implementations that we're going to talk about in this escapade here. There's the Windows dialer, which does allow you to make a PPP connection over a serial interface, but we primarily care about this program called PPPD. And this is the standard PPP daemon that literally everything in the world uses, except for, like I mentioned, a few operating systems that we could call edge cases. So these arguments are all the same. If we scroll down to the bottom, you'll see that this was written by Paul Macaris. That's definitely not how you pronounce that guy's name. Anyway, this is what you use to establish a serial PPP connection. Now, if you're dialing out, there's two ways that you can dial out. You can use a dialer script that PPPD will automatically use, or you can use a terminal program, connect to your modem, dial into your, for some reason, still using dial-up internet service provider, run the command on their side to start PPP, or just log in, but sometimes it's automatic. Or even just as soon as it answers, it will dump you straight into PPP, which we will look at what that looks like in a moment. But you can do that, and you're good to go. So, let us begin. So this will be the client, and this will be the server. So in order to serve PPP, we do PPPD local, meaning it's the same thing as the -L argument with SLIP, meaning don't try to use any fancy terminal control signals on the serial line. Debug, so we can see the session coming up. No detach, so don't fork off in the background and run away. Passive, actually no, we need this to be active. And then no CRT SCTS, meaning no modem control signals. And then we need to specify the IP. Actually, we'll enable IPv6, so plus IPv6. And then our address, 108.1.8.0.1, and then their address, 108.1.8.0.2. And then the serial interface, TTYS0, and then the baud rate, which doesn't matter because we're going at full speed. Now, if I do cu-l/dev/tty00, you're going to see, this is basically a terminal program, you're going to see the signal hopefully come through, and if for whatever reason it doesn't, then we have a massive issue. Okay, hold on a second, what's going on here? Oh boy. Yeah, that's right. Well, we'll try it anyways. So we will drop out of this. Ah, yes. Probably should use tip instead. Oh, wonderful. They got rid of tip. That's fine. We just won't... Actually, we'll do it in reverse. If we do that same command over here, which I will just show you directly transcribing. And then I use minicom over here. Oh, huh, interesting that OpenBSD's PPPD doesn't support IPv6. Very strange. PPP device is not available. Oh my goodness. Oh well, that's no matter. We will just use a different operating system for this demonstration. So I will go ahead and shut you down, which is not how you shut down OpenBSD. And we will switch to Solaris, because that actually has working PPPD. Okay, so we have two operating systems here that I'll demonstrate just to show you how commonplace PPPD is. We have Solaris 11 and QNX 4.25. I guarantee not a single soul will ever use this, but we're going to do something interesting with this. We're going to do QNX kind of like it's a dial-in ISP to an extent, and I will show you how that would work. Yeah, make sure you read the help. The QNX help is very good. This command that I ran here will start a login session on this terminal, so we don't even really need to care about this anymore, because if I do minicom-d/dev/tt, what is it, S1, let's hope it's right. There we go. We see this login prompt, and we can log in as root, and then we can identify ourselves that this is QNX. And what we will do here, oh, I don't have a clear command. Oh, that's going to suck. Okay, I best stop pushing enter. What we're going to do is we're going to arm a PPPD command over here, and then when we're ready, we will switch, and I mistyped my password. And when we're ready, we will run PPPD here on QNX over the serial cable, which we're viewing here on the terminal. And then, when we're ready, we will switch over, and we will, in theory, be able to bring up a PPP session here. So we will do PPPD, and then the same old that we've been doing. So local, debug, no detach, no CRT, SCTS. There is no IPv6 support on this ancient operating system that we are connecting to, so it doesn't really matter. 198.18.0.1, 198.18.0.2, and as you can see, we are on TTYS1, and then the baud rate we don't care about. Okay, so I'm going to hold this for a second, and I'm going to come over here, and, well, this is going to seem a little bit backwards, but because both sides of PPP can mutually initiate a connection, this works out great for us. So I'll do PPPD, and you can see that garbage on the screen. Boom. You saw that garbage on the screen there for a second. If you didn't, go back about 15 seconds and you'll see it. But this brought up a PPP connection. I'm going to bring this out of the way so it's a little bit easier to read. So let's talk it through. I hope you can see this mouse cursor. Unfortunately, I don't have this camera rigged up, so I can't just point on the monitor with a stick or my finger. But we assigned interface PPP0 to serial port COM2, so TTYS1. The first thing that PPP is kind of like a state machine, okay? The first thing it needs to do is do the link control protocol. So this right here is what it decides on what is valid and not. So can PPP control statements be compressed? Well, it would seem so. What about CCP? This is the compression control protocol. It has nothing to do with China. The compression control protocol will say, hey, do you support compression of any type whatsoever? So it will try, in this case, BSD deflate compression. And it will try BSD and deflate compression, which are the two algorithms that it tries to use. Then after that, it's going to use IPCP. So this is the IP control protocol. And it will attempt to do VJ compression. So do you support VJ compression? What in the world is VJ compression? Well, it's the guy who made it, Van Jacobson. And he came up with this very clever means of compressing TCP IP headers, which takes them down from quite a number of bytes, about 20, down to about 2 or 3 best case. So VJ compression really helps. However, CCP is its own compression algorithm. So we're relying on the TCP IP stack to do compression rather than the PPPD code. Okay? Do you support IPv6? Well, obviously it's not, and we're going to see what happens there. And then it's going to say, hey, I am 192.168.1.134. Now, that is the Ethernet address of that QNX machine, because if I switch to it over here and I bring up another terminal so you can see, I netstat-i. I don't know what they call the interface on here. Yeah, there it is. ifconfig en1, you'll see there's the interface. However, Linux here, because you see where sitting is like, nuh-uh, you're not doing that. You're doing 198.168.0.2. So it's like, okay, yeah, all right, that's fine. But we also get a protocol reject. So we get a protocol reject for compression control protocol. And we also get a protocol reject for IPv6 control protocol. So we don't support IPv6. It will then acknowledge, okay, I got that address, and I understand that you are 198.168.0.1, and then at that point, we're ready to go. So we can come over here to another TTY, and if I could do ifconfig PPP0, I can then ping 198.168.0.2. I can telnet to it. Oops. I forget how ridiculous QNX is sometimes. And this also has a corresponding... Okay, great. Oh my gosh, I'm gonna have to scroll. This is horrible. Okay, you can see it also has a corresponding interface. So we now have a very simple working PPP connection on an operating system that not a single soul has heard about. But we can do better than that. Let's do one on Solaris too. And it's basically the exact same method. Oops, I forgot that numpad enter type special characters on here. Alright, can we use backspace? We can. Can we clear? Yes. Alright, so we will do basically the exact same thing. However, on Solaris, you need to understand what the COM port device is. So that is exactly the same as it is on OpenBSD. So here's our TTY00, and if we look at this, we have TTY00 mapping to COM1 on Linux, so this works out great for us. So we will do the exact same thing we did before, except we will just establish a connection automatically on both sides. Except, rather than hogging up our own terminal for PPP, we will use dedicated leased lines rather than a login shell, which is really what I did before. Because if we just type PPPD, it's going to put garbage on your screen because it's trying to use your terminal to establish a connection, because that's what you would do way back in the day. You would just run PPPD and then it would load up a configuration file from /etc/PPP somewhere, which there it is. So there it is, options, and then there's also chat secrets and PAP secrets, which we will look at later. That's for dial-in security. But it's pretty simple. It will just automatically load option files, but if you have a dedicated lease line, you might want to do this a little bit differently. So fortunately, it's not much harder. So PPPD, local, no detach, debug, no auth, which sometimes you do need to specify on newer versions of PPPD to prevent it from wanting to use authentication. The inverse of this is require chap, and sorry, I misspelled that, or require PAP, or require MSChat v2, or something like that. And you can check the man page for that. They're all the PPP man page is great. And we also need to enable IPv6 because we can, at least I think this version of PPPD supports it. It may not. And then we will let Linux configure that address for us. Oops. So let us do that. So exactly the same thing. I should probably have entered that as well. It's not unusual for PPP commands to be hideously long. That's actually quite commonplace, you'll come to find out. Okay, and we should be good. Okay, and then they will negotiate. Usually it takes a second for that second LCP packet to come through. And you can see that, for the most part, this worked a little bit better. We now have IPv6 support, and we also have deflate compression. So this is full real compression. Now, you can also identify, with the LCP ident operator, you can identify who you're talking to if you for some reason don't know, but we are using VJ compression, and we are using deflate compression. So this is like compression to the max. So the effective bandwidth required here will actually be a little bit lower than one might imagine. Okay, well this terminal's hogged up with the other PPP session. So if we do ifconfig PPP1, because remember this used PPP1, we can do all the exact same stuff that we were doing before. Let's see if I have inetd running on Solaris. Why yes, we sure do. I doubt this will work. Not on System Console. Go figure. Can I log in as my user account? Nope, I never created it. Oh well. But nonetheless, we can do that from here. Let's see if we have virtual consoles. Yes, we sure do. So we can ifconfig PPP0. Nope, ifconfig-A. There it is. It's SPPP0. That's the thing, is every now and then you'll run into issues where it's not necessarily a uniform device name. Now, Solaris is very weird because it has separate ifconfig output for both IPv4 and IPv6 support, but actually, you know what? Let's be fancy. Let's use that IPv6 support that we finally have here. So FE80, oops, 5D0B, 4C41, F128, 967B. Okay, and we can log in here, except that's not going to work. Oh my gosh, I hate when backspace isn't set correctly. Okay, so we're, that's right, the stupid init system that I'm using doesn't even support who, and I don't even have who installed and functioning either. But we can ifconfig PPP1, and we can see, lo and behold, we are actually telnetted into that link local address, as you can see there. So it's really not rocket science, it's pretty simple. But we're just getting started. We're just getting started. I hope by now you understand how this worked. We established a link layer protocol that is Ethernet-like over a serial cable, and we have carried multiple different protocols over it. However, Linux is like the jack of all trades, master of none. Yeah, look at my ridiculous ifconfig output. We have multiple IPv6 addresses, which, okay, that's not so common. But we also have an IPX address, and I can cat/proc/net/apple or atalk/interface. We have an AppleTalk interface configured on ETH0. We also can look at our DECnet address, which is whatever it's supposed to be. We can look at our DECnet neighbors, and you can see that our router peers 1.50, although this being 1.44 is our address, 1.100 is my actual router that I'm using to get out on the internet. So, yes, my router speaks DECnet. It's kind of weird. So, we have a wide array of protocols that we can talk on here. However, Linux only supports IPv4, IPv6, and IPX over PPP. It's the thing that most people know, or most people don't know. But how are we going to do this? Well, I'm glad you asked. We shall employ something known as PPPoE. And in order to make this easy, I have configured a PPPoE access concentrator on my router with the simple username and password that we will use for this demonstration. So if I bring over a console on my router, I did the debug PPP events. Also, you need to do term mon in order to do this here. You can see we have various interfaces. We have vi3, so if I do show int virtual access 3, sorry, for those of us that can type competently, this is speaking, stop scrolling. Oh my gosh, okay, hold on a second, we're just gonna grab it. Okay, you can see we are using ATCP, sorry, you see the line that says listen? I apologize you can't see it, but this is gonna show us what protocols this is supporting, okay? So, this interface here supports ATCP, that's AppleTalk Control Protocol, IPXCP, IPX Control Protocol, NBFCP, that's for NetBIOS frames, OSICP, which is for the OSI network stack, and then DNCP, which is DECnet. Please don't make any DN jokes, I know what you want to say. However, only IPCP and IPv6 ended up working. So you can also see that this virtual access interface 3 someone is trying to do DECnet, NetBIOS, and IPX, but it's not happening. So let's make it happen. Now, there are two ways to do PPPoE on Linux, and just for fun, I'm going to invoke Wireshark, and I will demonstrate to you what PPPoE session bring-ups look like. So I will filter for not IP. Actually, I will filter for not TCP, and I will bring over Wireshark so you can see what's going on here. So my network is a very bizarre thing. So the first packet we got was an IPX packet, and I hope you can see these address fields reasonably well. And we get some ARP, get some NetBIOS over UDP over IP. We got some spanning tree, got some LAT, some local area transport. That is from my router advertising a remote console service. We got some IPX. We got a DECnet router beacon from 1.12. That is a Unix machine. And then there's 1.100. So this is a router, and this is also a router beacon. Got some IPv6, blah, 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 blah. Maybe we'll see some RTMP. There's some Apple Talk. And every now and then you'll see a DEC mop remote console. But in other words, I have a very questionable network that I'm currently... Oh yeah, here's some SNA packets. But I have a very questionable network, you could say. And that means that I have a lot of different protocols I need to carry because I live under a technological rock and I never made the jump to TCP/IP. So, how in the world would it be possible to start carrying more than TCP and... more than IPv4 and IPv6 over PPP? Well, we actually have to wind back a little bit, and we need to talk about how we're going to bring up a PPP session to the router. We are going to employ a technology called PPPoE. So we're going to start filtering for PPP, but no, we're on an Ethernet interface. There are two ways on Linux to dial out to a PPP VPN. Sorry, not a VPN, but I mean, I guess it's kind of a VPN. It's really not. There's the PPPoE command, which if we do this, you're going to see something very, very familiar. Oh, you will see if all is well. Aha! Router 1. Does that sound familiar? It should. Router 1 is the host name of my stupid router. And we see the negotiation stages of PPP, and you can see that my router is calling out to my Linux VM here, saying, "Hey, I'm alive. Let's talk." So I support CHAP. I support multi-link, yada yada yada, so on and so forth. But if we could somehow get that PPPoE command to work with the PPPD command, would be golden. And sure enough, we actually can do that. So we'll do PPPD PTY, that same command. We won't care about... Oops. What PPPD am I killing? We'll just kill all of them. The end. Too bad. You're gone. You're gone. So we're keeping it simple with this one. Okay, there we go. Termination app. Alright. Let's try that again, except this time I won't prematurely push enter. PTY, PPPoE, -I, ETH0, no detach, debug, user, VPN user, password. I said a really good password. I love PPP123. Hopefully that doesn't treat like a shell event. Let's see if this comes up. Actually, we will enable IPv6. So right here, plus IPv6. Okay, boom. That was rapid, and that was rather extreme. Unfortunately, I'm going to have to BG and scroll. So this is where it gets a little bit crusty. So let's look at the session negotiation. Because the beautiful thing about Wireshark, and when we're reviewing PPPoE sessions on Wireshark, is that we can actually make out the packetized versions of every single one of these sent, receive, blah, 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 blah. Okay? So obviously, we start up here with our LCP. Alright, good old stuff there. We do our CHAP login. So this one we actually did login on. So I've literally built like a fake PPPoE internet service provider here. Then it's going to start trying to spam out a bunch of different protocols to see, hey, let's talk with IP, let's talk with IPX, let's talk with DECnet, let's talk with compression, let's do IPv6, let's speak the OSI, let's speak AppleTalk, let's speak NetBIOS. Unfortunately, my woe is me modern version of PPPD, which we will inspect an older version which has way cooler features, it's going to reject IPX, it's going to reject DECnet, compression control, OSI, AppleTalk, and NetBIOS frames. However, everything else just kind of worked, and you can see that Wireshark will just automatically decode the highest, I guess you could say, the highest protocol in here. So we have IPv6 working. However, I can come over here and I can route del default, route add default gateway, and I need to show you what the interface looks like. So PPP is 0, you can see my destination address is 192.0.2.1, and I can ping google.com with this wonderful machine, or we'll keep it simple. And if I come down here, you'll see that there's some ICMP requests. For whatever reason, the name resolver decided to not work. But there you go. You can see that all will pretty much work, and it's as simple as that. Now, PPP does have keep alives. It sends these echo requests and echo replies every certain time unit interval. But what else can we do with this? Because it seems kind of performance questionable, I guess you could say, to use a pipe. I mean, at least I think it's performance questionable. So there is a better way to do this. And PPP actually supports plugins. So if we do PPPD plugin rp PPPoE.so, and we can actually look in /user/lib/pppd 2.51. There it is, rp PPPoE.so. Great, you can't see the cursor, but it's kind of in the bottom right. We will be able to use this for a true all-in-kernel PPPoE session. In other words, it's actually fast, which we kind of want. So no detach, debug, user, VPN user, password, I love PPP, which I totally do. And then boom! Obviously, this will technically be more performant, even if it seems kind of strange why that may be the case. The reason that in-kernel PPPoE using the plugin is going to be faster is because you don't have to switch between user land and kernel land. Here's the thing about PPPD. PPPD really is just kind of like a babysitter for the actual kernel PPP code. So in a way, when you're using PPPD, the kernel's doing all the work. And you can read the PPPD source code if you want to see how that truly works under the hood. It's very dependent on having a kernel that supports it. That's why we couldn't do OpenBSD, because for some horrible reason, I didn't configure the system to have a PPP device, okay? So we now have this working like you would expect, and we still have our PPP0 interface, same as always, except I probably need to re-add that default route. And it's the same as it ever was. What else can we do? What are some more interesting ways that we can bring up tunnels? Well, there are other means of doing PPP tunnels over IP. Now, PPPoE is great, but that's only if you're like an ISP. What if you're not an ISP? What if you're like trying to build an actual VPN over the internet? Well, let's look at PPTP. Now, this is obviously old and insecure, but it works nonetheless. Okay, so it takes a little bit of effort to go track down the PPTP client for Linux, but it's called PPTP. It looks like this. Now, we are going to continue our filtering of PPP packets because now we will really be able to see them, except we are going to filter for GRE or, oh my gosh, maybe I should learn how to actually use Wireshark someday. I'm so bad. TCP.port equals 1723. So we're going to filter for GRE, which will carry the PPPoE the PPTP session data, and then TCP port 1723, which establishes the connection. So PPTP works a lot like PPPoE with that user LAN pipe method, because I can just do this, and you will see, in a way, kind of the exact same thing that we're used to seeing. So you get to see that PPPoE, or that standard PPP session stuff there. So we bring this up and we say, hey, set me up a connection. So how about we support any kind of framing. This is the vendor of our client, and then say, all right, yeah, we're made by Cisco. All right, so your call reply, yada, 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 this will set up that GRE tunnel. And then boom, this right here will, inside of a GRE frame, contain our PPP session itself. And you recall back to that diagram that I showed in that PowerPoint slide deck, you can see that this is in fact exactly the same thing. So pretty simple stuff, not too terribly hard to understand, but how do we actually use this? Well, you can probably guess. The exact same that we've been doing. So we will just scroll up until we find our beautiful command here, and we will instead do this. So we'll just do PTY PPTP 192.168.1.1 no launch PPPD. Okay, and it's going to attempt to negotiate a session, and it was as easy as that. Okay, so up here, here's our real PPPoE session start. So we got LCP, chat, CCP, IP, blah, 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 all the control protocols for the protocols that we don't yet speak, but will try to speak. We'll at least try to speak IPX. And you'll see that this will work pretty simple as that. And this will do the exact same link control request and replies as you have seen on all other forms of PPP. But this isn't necessarily super secure. And also, this is like really old-fashioned, which I know seems a little bit ridiculous to call this old-fashioned, but I mean, this is a GRE tunnel. I mean, if you're using a GRE tunnel, you might as well just directly use IP or IPv6 inside of that GRE tunnel. We won't strictly look at that in this particular episode, but we will look at the logical successor to this here, and it is L2TP. So L2TP is a little bit more complicated to set up. It is actually something that runs in the background as a daemon and will automatically start PPPD on its own, so let's take a look at that. So we're going to use a program called L2TPD. Now L2TPD will spawn its own PPPD in the background, and if you read the man page, you will start to get a gist of how this thing works. You aren't really supposed to invoke it directly as a command. Like, you can't just run L2TPD and then boom, you'll see a PPP garbled text appear on your terminal. Unfortunately, you do have to actually configure it properly. So in order to configure it, we go to /etc L2TPD, and we will edit this control file here. So this will provide us with debug statements so that we can see what's going on inside, because we always run stuff with debug because that's what we like to do. And then we will create a tunnel called Cisco because we're talking to a router. Here's the destination address that we want. We do need to require authentication inside of the tunnel, not authentication of the tunnel itself. That's the thing, is L2TP allows you to authenticate the tunnel itself. However, that's rarely actually done. You always authenticate with the downstream protocol. In this case, this require authentication means, okay, we're going to make PPPD do its own authentication, which seems a little bit redundant. It's kind of weird. Auto dial means bring that up when we actually start L2TPD. However, we're going to need to edit /sc/ppp blah 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 in order to actually configure how PPPD is going to respond to this. So if I edit options.xl2tpd.cisco, these options files basically are just things we automatically feed into that PPP command. So we will accept the remote address as we always have. We'll require chat. We don't care about compression. We don't care about authorizing the remote machine because, well, we're the ones doing the authorization. Persist, make the tunnel stick around. Don't let it fail. Debug, MTU, yada yada yada, and while we're here, we'll enable IPv6. Okay? So, alright. Wonderful. Okay. Let me make sure I didn't corrupt my file. No, I'm good. Okay, so now we will do XL2TPD-D, but before we do that, we're going to come over here and we're going to do udp.port equals 1701 and fire. What in the world? Oh. The beauty of a temp file system is that that always goes to crap. Okay, so this is L2TPD's session initiation. So we did not ask for IPsec. We will demonstrate that, and it is extremely handy. However, otherwise, it's just the same old stuff that you're used to seeing. So we spun up a PPPD, and you can go check /var/log/pppd.log if you care, but I don't think that we need to care because ifconfig PPP0, there she is. And if we come over here and we do a debug, you can see that first L2TP needs to bring up its own tunnel. So there are all these weird opcodes, and for some reason they're called AVPs, which has nothing to do with aliens versus predator, but for some reason that's just what they're called. And then you can see there's your PPP, and then great, here's our downstream packet. So we always start with some good old-fashioned IPv6 neighbor advertisements and then multicast reports, because of course IPv6 loves its multicasting. Okay, so that was pretty simple to do, and for all intents and purposes it's running in the background, and we can just kind of leave it there. But we now have multiple different ways of doing this. However, look at us. We can sit here and we can decode the traffic. Alright, if I telnet 212.168.1.1, you know, I can just sit here and I can decode my telnets. Oh, hang on, that was a bad example. Let me actually do this so that we'll catch it. I can just come over here, you know, everyone knows, like, Wireshark 101, follow TCP stream. Sorry, there's the password I tried. Okay, so pretty questionable stuff. You would not want to use a raw L2TP tunnel. So how can we make it better? Well, we will employ something a little bit more secure. We're going to employ IPsec. But in order to do that, we need to make a lot of changes to some of our config files. So IPsec is essentially a wrapper over existing connections, but we're going to connect to a different Cisco router for this particular example. So we need to go edit our XL2TPD configuration. What in the world has happened to VI? Okay, I'll use the letter keys. Okay. And then we need to also go edit our options file. Except this time, oh wonderful, this is happening again. Except this time we need to do test user, and then our very secure password is going to be password 123. Okay, so, oh great, why do I keep getting, this is why I don't fly blind. You know what, I'm sorry y'all. I do apologize for having to shrink the font size, but I am so tired of flying blind. Okay, hurry up. There. Finally, we can see what's going on. Okay. Now, if we do XL2TPD-D, oh, hang on a second, we're going to have to kill the old one. This right here will bring up an alternate connection to an alternate router. So this is going to 192.168.1.86, which is a dedicated router that I keep around just for testing purposes and such. Okay, we'll clear you, and now we're going to do IPsec. So IPsec is very crusty to configure, and I will go ahead and bump up this so we can see again. Wait 30 minutes for the window to resize. We are going to edit ipsec.conf. Now this is the classic way of, oh my gosh, hold on. Sometimes you have to use reset to reconfigure your terminal. There we go. Now we can use the arrow keys like not a barbarian. And of course I need to scroll because you can't just paginate scrolling VI easily. Okay, so what in the world? Yeah, IPsec isn't exactly easy to configure, but once you understand it, it's extremely easy to get the gist of, okay? So let's say that you have the following statements, and we need to actually come over here and start up a telnet session on our router. Why am I not showing you this? I don't know. If I do show run, I'll just give you a brief escapade how you would configure a session here. So we'll have two crypto ISACAMP policies, one using 3DES, one using AES-256. As you can see, AES-256 right there where it says ESP and IKE, those are what this is going to map to. This is where we set our pre-shared secret, which we'll look at how we do that on Linux in a second. And then these right here are our transform sets that associate both set 1 and set 2 with 3DES and AES-256. These are running in transport mode, not tunnel mode. And then we need to come up with this map here. So this right here will associate our transform sets with our map, and then this right here actually engages the map, and then we come down here to fast Ethernet 00. Come down here, there will be a crypto map outside, blah, 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 blah. And then we need to actually configure the real interface. So you need to configure virtual template 1. You also need to configure loopback 1. Loopback 1 because of something called unnumbered processing, and I'm not going to sit here and explain how you set all this up. I could talk for hours on how to configure a true multi-protocol VPN server on Cisco iOS, but you do virtual template 1, you do loopback 1, and then you need to come up here, you need to do VPDN enable, VPDN group 1 for PPTP, group 2 for L2TP, and that's basically it. And then you can configure ACLs if you want, any reasonable form of security. But if that completely went over your head, I understand. But rewind that and just copy and paste those configuration statements into your router, and you will have a multi-protocol VPN server. Obviously, I rig up my stuff for all kinds of crazy protocols that nobody uses anymore. But, you know, just don't enter the IPX and CLNS and DECnet and AppleTalk and other such commands if you don't need them. So here's how you set this up. So we're left, okay? So our left protocol and port that we want to secure is we want to secure protocol 17, which if you go check/etc/protocols, go to, there it is. You see UDP, I was already scrolled. You see UDP has the protocol number 17, okay? So we're securing 17, and then because that protocol has ports, we'd use 1701, which is the L2TP port. If you want to use GRE, you'd use the GRE protocol number for that. Our left subnet, anything. Our address is this. So this is the address that the packets are coming from. We want to talk to 192.168.1.86 on protocol 17, UDP, port 1701. Right subnet, we don't care. We want to use ESP, so we're operating in encapsulating security payload mode. If you remember back to the PowerPoint slides when we talked about this. For our Internet Key Exchange, we're doing AES-256 SHA-1 mod P1024, which if we come over here and do a show run, which even though I already had scrolled, for some reason I'm going to do this again, this statement, group 2 corresponds to SHA-1 mod P1024, okay? This cryptographic stuff is not going to be the subject of this video in any great detail, but these are just the standards that everyone knows and loves and cares for. It's in other words, as long as you can map between the two of them, you're good. Our write ID, this is what, in theory, if the remote side is doing some kind of impersonation crap, we don't care, so only talk to this address. Simple as that. Now, we need to configure the secrets. So edit IPsec.secrets. If only I was in the right location. I am. I just need to scroll up. This is amazingly ridiculous. I should probably just change the VTY text size. So this is us. Okay. And this is them. So this is their address. And then this is the key. Alright, so you come over here. Boom. This is the key. Now, the way that IPsec works is it essentially stacks on top of it. So I'm going to do ESP or ISACAMP, and because we're on the same LAN, we won't need to do any NAT traversal, so it won't start out with UDP. I can do IPsec help, and you'll see the various commands for this IPsec command. This is from a package called StrongSwan, and this is the legacy way of configuring this, because, well, legacy, in other words, the way that people know. So IPsec start, okay, that will come up. IPsec status, we don't have any security associations, so I'm going to do IPsec list, Never mind. We'll just do IPsec.conf so we can get a gist of this here. Let us examine. So the name here is going to be L2TP-Cisco, so do IPsec up L2TP Cisco. Okay, so the session will establish. This is another amazingly hard thing to configure if you don't understand what you're doing, but if you copy and paste what I've provided you, you'll be able to get this to work with ease. And the best part, if you port forward ports 500 and 4500 on your router, this will just work over the internet. It's just very, very easy to get this to work. However, I should remark, by the way, Windows really likes doing its own weird IPsec stuff, and we're going to look at that in a second, what it looks like to configure an IPsec VPN server on Windows. We're also going to go back and look at the the Windows dialer, possibly. I hope we get some time to do that. I don't want this to go on for too long, though, because this is already, an hour and a half long, so yeah, you're in this for the long haul. I apologize. But now, at this point, wait, gotta scroll up. Oh my goodness. Come up here, XL2TPD-D, but the packets are opaque. Even though we know what the security key is, this is the key, and you can sit here and you can come to protocol preferences, encapsulating security payload. Not there, sorry. Come over here, and you can just punch in a security association, but sometimes it doesn't work. Most of the time it doesn't work. It's very finicky to sit there and try to plug it in and get it to work, but we are doing a IPsec VPN. This is carrying PPP inside of L2TP inside of IPsec, and you know that it works because every now and then you see it ticks for those PPP LCP echo packets. So we can't, if we know that, we know what this is. So yeah, a timing analysis already has revealed that the insides of these opaque packets is a PPP session, possibly over L2TP or over GRE or over something else. So it's extremely simple, though, because if I do IPsec, IPsec down L2TP Cisco, and then I do XL2TPD-D, it will bring it up in plain text, okay? So make sure that when you're doing this, that you actually legitimately go through and do the IPsec up, or just have it automatically start. So do be mindful of that. That matters a fair bit. Okay, now we're going to look at using some older protocols because, well, why the heck not? So I remarked before that we would use the PPPoE utility, and we're going to do that again, except we're going to use a bit of an older PPP client that supports IPX. So despite all of our fancy frills, we are not going to be using the Roaring Penguin PPP utility because this old version of PPPD, which I have wonderfully named PPPD Old, is just that. So we're going to run this on a PPPoE session, but we're going to do something a little interesting. We're going to enable IPv6, but this is also going to respond to IPX control, okay? So we'll see what that looks like here. So username, or yeah, user, VPN user, password, I love PPP. We'll see. Okay, IPXCP didn't work. Hold on. We will need to read the man page for IPX. So IPX, yes, we just type IPX. Okay, so I modified this such that it doesn't complain about not having IPX support in the kernel. So whoop-de-doo, you can see that IPXCP came and went, and believe it or not, we are going to get IPX packets. So you can see up here that IPXCP acknowledged, so you can see our network node. The remote node address is 189. Blah 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 blah. So if I come over here and I scroll up, we can actually go cat/etc/proc/net/IPX/interface, and you can see PPP0 lo and behold, has an IPX address. Keep in mind, this is not on some 100-year-old version of Linux. This is like, well, it's pretty modern. And we can also look at routes, because PS, AUX, grep, how about IPX? We actually have IPXD running. So you can see that I have a whole variety of remote router nets plugged up here, and that's because you can see that this network 189, that's the directly connected one. So if I come over to the router, which I don't actually have a session up for, but if I did and you did show IPX networks, you'd see 189 corresponds to that virtual template interface, which for us means PPP0. So you can kind of sit here and use this, like, I forget what the command is. Maybe it's ncp serve? No, ncp serve is the actual server. How about nw? Let's see, nw serve? No, nw serve is the network. Oh my gosh, oops. Alright, how about it's one of these. One of these we can use to browse other IPX nodes on the network to demonstrate that it does work. How about IPX route? How about netstat -r we won't bother with it. Anyway, the point is this is working. Oh, and I believe the command is slist. Aha, yeah, so it's not gonna really demonstrate appropriately, but there is a no network file server out there on the network. So that's great and all, but how do you dial from Windows? Okay, this is a little bit difficult to do because simply of how cumbersome this tends to be. Hang on, I need to see what COM port I'm eating up here. Okay, so COM2. So we will wait on QNX to die, and by die we will just force it to die. I will configure a Windows XP VM to operate on this COM2 here. So let me bring that up, and we're going to explore how the dialer works, and we're going to serve dial-up connections from Linux. Alright, so this is going to drive me insane. I mean, it's not so bad, but let me show you what I'm doing here. So I'm in /etc/PPP, and Windows is going to want to do a sign-on regardless. Oh, by the way, here in the background, this may seem a little bit ridiculous, but I don't know if you knew this about Wireshark, but it actually can decode IPX packets inside of PPP. So here you go. Here's like general response, you know, service advertisement protocol. So this is going over PPP, and if we browse, you can see that we have a Linux VM. So this is a Novell file server emulator, Win 2003 server. It's exactly what it sounds like this. And also we're doing NetBIOS over IPX. So pretty much any IPX broadcast packets are propagated, at least I've configured it, to beacon through tunnels as well. Okay, so here's like various Windows NT 4.0 era servers that are beaconing through. Okay, so the Windows dialer wants to do authentication regardless of who you are. Even if you try to say no authentication, it just straight up won't work. So you do need a way to accept this. So here's how this works. So this is the user we want to allow in. This means anyone can connect and use this user. This is their password, and this is the IP address that they're going to get, rather than getting an automatic one. So let us play Pong. Was it 1, 2, 3, 4, 5, 6? Yeah, okay. There we go. So we'll wait on that to come in, and we will configure, and I need to get it to change the display resolution automatically whenever it decides to do that in 20 billion years. Slow piece of junk. We will need to do something rather drastic. Because the Windows VPN, the Windows dialer client is kind of ridiculous, we're gonna need something. Hang on a second, I'm pulling something up on a display you can't see. We're gonna need to configure a chat script, and let me show you why you need to do that. Are you ever going to work? You blighting piece of garbage. This is just gonna get worse, isn't it? It is gonna get worse. Oh, wonderful. Wow, I love it when VirtualBox does not work. And I love how slow this is. I'm dragging the window. What's going on? You think I'm on a slow computer? I'm not. There, okay, finally. Better to have it full screen. It looks more consistent. So we're going to configure a RRAS dialer connection on here, which is allegedly hard, but I don't know why people think that's the case. We're going to delete this, and we're also going to go into phone and modem options and delete that. So we'll come over here, phone and modem options, modems, remove. Okay, so we're going to add a modem. Select it from a list. Remember, we're doing basically a no modem cable in a way. So select it from a list. We want to do a communications cable between two computers. We're doing it on COM1. At least I think it's on COM1. See, there you go. It's on COM1. All right. And Windows will install your modem. And then, when it's all said and done, we'll need to go actually then change a ton of settings, because if you thought this was going to be easy, boy, you are in for it. Let me show you what you have to do. So, open up the properties of this. Wait 20 years. For people who are trying to follow along at home. Properties. Okay, finally. Alright, I was about to pause the recording while we waited for it. So, you need to set the maximum port speed to something reasonable. It doesn't matter, it's a virtual machine serial port, but we'll do 9600 baud in case VirtualBox decides to do something stupid. Diagnostics, we don't care about that. Default preferences over here, this will allow you to override the port speed in another place. However, we want no flow control because it's a null modem cable, and most of the time you do flow control none. This right here allows you to set data bits, parity, and stop bits if for some reason you're doing something different. And then there's nothing over here that matters. Okay, that was for the modem. Now we need to add a connection. So we're going to create a new connection. We're going to connect to the internet manually using a modem. ISP name, testing, I guess. All right, phone number. Well, everyone remembers the song, 867-5309. Okay, we'll allow anyone to call out. Our username and password. This corresponds to chat secrets, or PAP secrets if you want to do unencrypted password. But it's test user, password 123, password 123. Do not make this the default internet connection. It will drive you up the wall. Click finish, and then device missing. So you will need to... Why does it think the modem is... disappeared? What? What is going on? Oh my gosh. Okay, let's delete that and try that again. All right, create a new connection. Okay, if this happens again, I don't know what to tell you. What do you mean device missing? The modem's right there. I don't know how that's possible. Maybe I also need to create a modem from the dialog? Yeah, because I know it will prompt you to do that. Oh, we're gonna get this. Alright. We're going to connect directly to another computer. Okay, no, that's not what you want. Connect to the internet. Manually. Yeah. What? Modem removed. Device unavailable. COM1. Do I seriously need to reboot for this? Okay, you know what? I'm like hell-bent on getting this to work. So let's try this again. Alright, communications cable. No, we want this to only work on COM1 or it will just freak out. Generally, the telephone API or the telephony API system works, but every now and then it will crap out, and this is a good example of that. However, it's a lot more reliable on Windows NT systems than it is on like Windows 98. You should see how horrible that is. You don't want to know. And of course, we'll pause this, you have to wait. Okay, that took a minute and a half to open. Port speed, 9600 baud. Okay. Change the preferences. Flow control, 9. Device unavailable, blah, 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 blah. How is that possible? How do you miss a modem? You know what? 0 baud is what I use. Maybe, just maybe, we can get this to work. So, this right here, allow unsecured password means to use PAP. Require secure password means only use chat. Oops. You can also do a custom thing, and this is just the easiest. So, optional encryption. This is what you actually want to use. Understand that some of these you may not have configured appropriately, but we are going to use chat, and then there's a long command that we need to enter. Networking, we're using PPP, but if you want, you can use SLIP, but we're going to do PPP. We'll negotiate IPX, because we're going to use that old PPPD just for fun. Client from, okay. And in theory, when we reboot, that should work. So I will restart this. Alright, so about 2 hours have elapsed since I paused the recording just there, and I finally figured out what the problem was. The problem is I was using a busted Windows XP installation that somehow had corrupted modem configuration environment. So in order to get this to work on a newer version of Windows, this is Server 2008, as you can see down here. However, this is also applicable for newer versions of Windows as well. You will want to configure a generic serial cable, communications cable as they call it, between two computers. Configure it, make sure the maximum port speed is something that you want. Uncheck hardware and error control. Then you'll come over here, and if you wish, you can enable software compression. Okay, so that right there, that's like the compression control protocol deflate compression. Oops. And then here on security, do advanced, do settings, and allow these protocols. If for whatever reason your dial-in concentrator doesn't have any of these protocols, you can just forbid them or just straight up not allow them. It's your choice. For networking, you have the option to use the default gateway on the remote network. Only use that if you actually intend for this to be your primary internet connection. Otherwise, don't. Now, due to the way that IPv6 CP works, it only negotiates you a link local address. Now, I had someone ask about this actually a moment ago in the interim time there, and if I come over here and I find a IPv6 CP configuration request, you will see where these interface addresses are derived from. They're derived from this interface identifier, which is kind of like a MAC address. So when IPv6 CP sets up both sides of the session tunnel, it's essentially giving you two link local addresses. You don't really get a globally unicast routable address using this. You would want to use some kind of other static configuration. The recommended way to do that, by the way, and we will explore this possibly here in a bit if I remember to cover it, is to use DHCPv6 and SLAC. Okay? So there is no true static address configuration. Now here on IPv4, if you click Advanced, this Use IP Header Compression, this is VJ compression. Okay? So in knowing that, we will then need to configure our Unix dial-in machine. Now this is very difficult because if I run Minicom so that you're monitoring the serial port and I come over here and I dial, you're going to see that it tries to do this client, you know, I don't know what's going on here. Like, why is it saying client? The answer is that's not what you need. You actually need to reply client server when this happens, okay? And we can actually do this, okay? So we can do client server. Sometimes it works, most of the time it doesn't. You usually have to paste it in. And if that ever occurs, you will be able to start up a PPP connection at that point. So obviously we want some way to automate that because that's ridiculous. Well, the answer is to create this file. You can name it whatever you want. I just name it winclient.chat. and you're going to wait for 3600 seconds, and whenever you see client, write back with client server, and then boom, we're connected. At that point, we're ready to pass it off to PPPD. So in order to use this, you need to use this relatively long command. So let's explore what this means. This is the pretty standard stuff we've seen so far. Require chat means to check chat secrets in the /etc/ppp directory for your username and password database. Plus IPv6 means you want to enable IPv6. And then connect, this right here will allow you to run a script in order to essentially either run a chat script or run something to initialize a modem. In this case, you need to specify the full path to the chat program. Don't ever assume that it will work out of the system path. And then here's the file that we're using, this winClient.chat thing. Here's my IP address, here's their IP address, and then here's the terminal. Okay, so we hit enter here, and then we come over here, and we dial. And then, boom, it's as easy as that. For some reason, people seem to think that it is like unbelievably impossible to do this, but I don't really know how or where their concerns come from. It is truly pretty dang easy to do this. And if we come over here and we look at the status, you'll see that we're obviously not using DHCP. We didn't engage NetBIOS because we didn't care, but we did get a local IPv6 address. Oh, hang on a second. I just realized something. You see this here? 117.18.0.2. I need to hang this up because I made a fatal mistake. If we come over here and we look at chat secrets, you'll see that this address here is what takes precedence. So I need to change this to 198.18.0.2 because that's what's in this here. Now, if you want, you can actually just kind of, sometimes you can leave that off. Okay, in this case, you can't leave that off, so we'll leave it on there. But whatever this address here is, you can just put in a bogus address for this, or one that never gets assigned, because whenever someone calls in, they're going to get their IP address. If you leave off the IP address in chat secrets, it will default to this address that you see here. Okay, so we'll start the chatting, and then, okay, well, we're talking PPP. Note here that CCP did actually work. So this is doing both compression, even though this did not engage any compression, it will attempt to procure that. Now, let's look at something that I think is pretty interesting. If we do TCP dump -I PPP0, and we come over here and we spin up, we'll need to spin up some kind of terminal client. Let me open that up. There we go. I'll save you from that horrible realization. Log in as user and password or something. There we go. You can see that this is technically compressed TCP IP. And this is a little bit interesting to see, but any sort of TCP IP stack in the Linux world will automatically decompress any of the available VJ compressed protocols. And we're going to look at what VJ compression looks like here in a second, because we can also log out, come back over here to our command shell here. We'll hang up here on the dial-up session, and we will actually, let's go here to Network and Sharing Center. We will connect to a network. We will set up a new connection. We will connect to the internet, create a new connection. Hang on, this may be a little bit difficult. A dial-up connection? This is a little bit cumbersome to figure out. Oh, there we go. Oh my gosh. You use an existing connection. And we're going to do PPPoE. So this is going to that Cisco iOS router. So it's going to be test or VPN user. Sorry. And then I love PPP 123 bang. All right, so we're going to come over here and we're going to restart our captures. For this, we no longer have Linux in the picture, and this, in theory, should work. And this will provide a default route out to the internet. So it is going to try to test the connection, but it is going to find itself to... Okay, there we go. So we're good to go. We can browse the internet. Let me guess, Internet Explorer is going to open. Of course it is. Why do I need that? Okay, so that works great. You can come over here and you can manage network connections, and this is a PPPoE connection. However, I want to demonstrate something here. If I come over here to properties, I can enable pretty much all of the ridiculous options here. So I can enable VJ compression, I can enable the Windows networking clients, yada yada yada, PPP settings. But yeah, we're going to negotiate multi-link for single-link connections, because a lot of people seem to think that multi-link PPP is like hideously difficult or something. Guess what? It's not. Oh, I thought this remembered. Okay. I love PPP. Boy, I sure do. Okay, here we go. So we're going to bring that up, and if we come over here and we look at the status and we look at details, okay, well, unfortunately on this version it doesn't work. So by all means, let me just open up my... You're not going to be able to see me do this here because I'm looking on the wrong monitor, but I'm just going to queue up a dial-up connection here on... Oops. I forgot I changed that there. Let's actually try this here. Oops, I did actually mistype that. So now we're running 2 PPPoE sessions on the same physical Ethernet adapter. So to settle a myth that you can only have one PPPoE connection active per Ethernet port is not true. I don't know why this is taking so long to complete the connection. I guess it's just having a grand old time. But if I open up the View Network Connections dialog right here, and I show you this here, why does it not think that it is working? You can see I am negotiating multi-link for a single-link connection. Actually, I bet I know why this isn't. There we go. It just finally decided to work. And if we come over here and I do status and bring you over here and do details, you will see that... Okay, where in the world is it? Somewhere you can... yeah, here it is. Multi-link framing is on, okay? So we're going to hang this up. But over here... go figure, right? It's the exact same thing. From the command prompt, if I ping some random address, you will see that in this particular instance, because it's just a single PPP link, it's not going to do any clever fragmentation. But the way that multi-link framing works is through some really clever fragmentation techniques, okay? So you can do standard dial-up and you can do PPPoE over this here, and for the most part it just works as is. It's relatively simple, it's not gonna make you go insane, and it's a reasonably simple protocol to understand. Now, I mentioned that we might also cover some other interesting things, such as how does IPv6 auto configuration work. Well, now that we actually have an example of that occurring, we can come up here and see that my machine will send out router solicitations. However, you aren't really supposed to use that. I know it seems kind of strange to think about, like, how in the world are you supposed to do a router solicitation if you only have a link local address? The answer is you need to do some kind of IPv6 only network address translation. It could go from a link local address to a globally routable address. And so that's one of the options that you have when you're setting up a PPP IPv6 dial-in system, which you should totally do. There is nothing at all stopping you from doing IPv6 over dial-up. Just because it's sold doesn't mean it doesn't have to work. But I also should probably give you an example of what multi-link framing actually ends up looking like. Here's a good example of a fragmented datagram here. So there's a special fragment flag here for the first fragment and then for the last fragment. So these right here, these never got reassembled, but you can probably sit here and analyze that and figure out what it's supposed to be. If I had to guess, it's probably the first time. Yeah, it's probably the first time that they're using a unique packet to discuss, because 18, 19, 20, 21. So it's just Wireshark not properly reassembling the fragments there. But nonetheless, this works, and this can work fine over the internet. There's nothing to impede you from having this work over the entire internet. So if you have multiple WAN connections and you want to build a site-to-site VPN that runs at an appreciable speed, you can just do that with this, really. People make it out to be a whole lot harder than it actually is. So I do encourage you to try to use the multi-link PPPoE scheme. Well, not necessarily PPPoE, but to at least try to use multi-link PPP where applicable. So, in all honesty, I think that these serial line networking protocols, going from demonstrating how we went from this command here to an L2TP and PPP tunnel, as well as doing it over IPsec, I hope that this really was informative, because I know that a lot of people really struggle with trying to wrap their head around how VPNs really work. And I have composed some truly long guides on how to set up a whole manner of ridiculous VPN tunnels. The answer is PPP is pretty much a universal protocol, and you can easily wrap it onto a pseudo TTY on basically every operating system ever. So I highly encourage folks to use it, and I also highly encourage you to leave any questions you may have. If you think I said something wrong, please correct me and let me know. I know we didn't really cover IP/IP and we didn't really cover GRE, but I suppose I can go ahead and demonstrate that just for good measure, because I feel like some people may find it helpful to have a brief explanation of how GRE tunnels work. They are maliciously simple. And IP/IP tunnels are also quite simple as well. However, to do this, I will set it up on, you know what, I think a FreeBSD machine will do. So we'll save the OpenBSD, but we will do FreeBSD. Please wait while my server answers my calls, and I will go ahead and queue this up and write an example. Okay, so the best way I think to demonstrate this is to just do and directly show. So we are going to stop this capture initially, and we are going to prepare a tunnel. So there's two ways to do the tunnel configuration. The first way, I'm referring on Linux here, is to use the IP command, but you can also use the IP tunnel command. So it's kind of like ifconfig, but just for good measure, I'll show you all how to do this both ways. Okay, so you do IP tunnel. Okay, so there you go. Those show the existing tunnels. We are going to add mode IP local. This is our local address, as in our local on the internet address. Okay, and then our remote is going to be 192.168.1.145. Okay, and if I do IP tunnel, you will see it being there, and it's of mode IP/IP. Okay, so if I do ifconfig IP 0, we then need to set the interior of the tunnel. So we'll do 10.0.0.1 dest adder 10.0.0.2 up. Now we'll come over here to FreeBSD, and there's two ways we can do this. One, we can use NOS tunnel, which actually provides a user LAN tunnel, or two, we can use the GIF device. The GIF device is an in-kernel solution, and it's way faster than doing anything else. Okay, so we will do this with the GIF method because it tends to be a bit easier to understand. So ifconfig GIF 0 create. Now, GIF tunnels, by the way, can operate in any mode. It can do IP/IP or pretty much anything else. So it can do a SIT tunnel, or it can do a 4-to-6 or a 6, or it can do a 4N6 or a 6N4 tunnel as well. So for this, you can use either the GIF config command, which we obviously no longer have. So the correct solution is to do this. Sorry, I pressed the key to pause recording. This is what you'd do. Okay, before I take this any further, I'm going to show you how to do this. So you do ifconfig GIF 0 create, okay, and ifconfig GIF 0 tunnel, my address, their address, and then these are the addresses inside the tunnel. So if I do ifconfig GIF 0, you'll see that this is working as a tunnel, and then that's the link inside the tunnel, and it always is going to have a relatively low MTU That's just a fact of life when it comes to this. I would recommend that you bump up the MTUs to the maximum that you can achieve. Start with your Ethernet MTU, subtract the Ethernet header, subtract an IP header, and subtract another IP header. So, for those following along at home, we are on Ethernet, so we have a 1500 byte MTU. Okay, so we need to subtract 14 bytes for an Ethernet header, 20 bytes for an IP header, and then another 20 bytes. So our effective maximum MTU is 1466, but we're not going to bother to change it. But we will come over here, and we are going to filter for ICMP packets. And we're going to continue without saving, and we will come over here, and we will ping 10.0.0.2. And you will see that this is going on inside the tunnel. However, these addresses are the final addresses that lie within the actual tunnel itself. These aren't necessarily addresses that fill the full duty of the tunnel, okay? So, if we come down here and examine, you'll see that we really have a double IP header situation, okay? So we have the outer header, this right here is what will go over the internet. The protocol number that we're carrying, come down here, it's 4. So we're carrying IP. And then it works just like that. You can, however, also do a bit of an alternate situation or an alternate solution here. So if I do ifconfig gif0 destroy, I can do this nos-ton command, okay? And this right here provides a userland solution. Okay, and then you can probably guess how this is going to work. Okay, something went wrong. Very strange. I might have messed something up. Just for good measure. Well, let's try it over here. I don't know what's going on here. The packets are being sent. They are going out. But... oh. I do apologize. I specified the wrong destination address. It should have been that. And now, in theory, we should get a little further. Oh, the source and destination address are the same. Wow. Perhaps I should start paying attention some. So the source address is this, the destination address is this, and then finally, the pings will start going through. And this is the exact same behavior, except it's being done with a userland program. So if you have some aversion to using that driver, you sure can. Now, the nos-ton command specifically allows you to override that protocol number because, and you can see the pings are now going to start timing out. NOS uses protocol 94 rather than 4 by default for its tunnel, so sometimes you have to adapt that accordingly. So just do be mindful of that. The defaults do change in various different places. Now, we can also do a GIF tunnel. I'm sorry, a GRE tunnel. GRE tunnels aren't too horribly difficult to create. So on FreeBSD, we'll do ifconfig gre0 create, ifconfig gre0 tunnel, and then it's the exact same arguments before. So this is my address, 192.168.1.145 to 192.168.1.107. Okay? And then ifconfig gre0 172.16.0.1, and then the target address, netmask. Okay, and if you want, you can do IPv6 as well, and it's pretty simple to do. But we're gonna come over here and we're gonna do the exact same thing, except we're gonna do IP tunnel. Hang on. There we go. IP tunnel add. I had to pull up my notes, make sure I don't get anything wrong here. So we now have GRE1. Okay. And we are now operating with GRE, okay? So we now have this generic routing encapsulation, and this right here says, hey, we're carrying IP. Remember, these numbers here, these are shared with the ether type address space. How do I know? Because boom, it's the exact same thing. They made it easy. GRE version 0 has a much smaller header than other forms of GRE, okay? Because this is a 4-byte packet. Other versions of GRE have much larger packet headers that may be a bit cumbersome if you're on some less than performant network architectures, so do be mindful of that. And as soon as we do that, it's all going to stop. So IP tunnel, I think it's destroy. No, it's del GRE1 and IP0. Now, if you wanted to do this using the IP command, you do this. It'd be IP tunnel add GRE0 mode GRE remote local. Same thing, really. It's modeled after it, so it's not too hard to understand. But with that, I am actually going to end it here. So again, even though there's a little bonus section, I didn't really intend on doing it. I figured I should have done it anyways. Do note that other protocols can be carried within GRE. I do have several examples, and I will expeditiously queue one of those up because there are a lot of protocols that you can carry over GRE that you might find to be a little bit interesting. So if I load up, okay, I'm going to have to stop this here. If I load up this capture here and I filter for GRE, you will see that I have some strange protocol here. These are DECnet and IPX packets within a GRE tunnel, which seems kind of hard to think about, but this one right here, this is DECnet. These right here, I believe, are IPX. Okay? So you can encapsulate other protocols. So at this point, you can pretty much build any network you want. And for all intents and purposes, you should try. This is really fun, really useful knowledge, and I highly recommend that you try to build a bizarre, odd network at least one time in your life. And you should totally build a dial-up network too, and while you're at it, don't settle just for dial-up. Make an ISDN network, make a T1 network. In the next video, we're going to actually explore how to do that. Okay, so I also wanted to go ahead and cover how you do this on OpenBSD on the off chance that someone finds it useful. OpenBSD probably has the most turnkey solution for this. It's literally just 3 files that you have to edit. So the target is, of course, like the Windows VPN client, the iOS VPN client, Android, so on and so forth. In other words, VPN clients you don't have to install, so it's pretty easy to do. So start by editing, actually go ahead and go here to /etc/nppd. Go ahead and edit nppd.conf. Make sure that you allow users to sign on as stored in this file. Here's where you specify the bind address. If you have multiple adapters, specify that here. This is, of course, the IPv6 bind address. IPCP, this is the range that you will be given when you connect. Here's the DNS server that is given to the client. And then if you wish, these will provide I guess you could sort of say kind of like a multiplex tunnel. You don't necessarily have to use this. The default is sufficient. So given that, we now need to edit nppd users. So here is our test user, and then our password is password123. If you want, you can specify an address here, but it needs to be within that range that you specified. Okay, now you need to edit IPsec.conf. So IC passive, we want to use ESP, running in transport mode from me, this is my address here, to anybody. This is a bidirectional rule. We want to use mod P2048. I think this is Diffie-Hellman Group 5 or something. It's one of the defaults that Windows supports. And then here's your pre-shared secret. This is lifted straight out of the documentation. My tunnel is private. Now, while you're here, go ahead and edit sysctl.conf. So make sure you allow IP forwarding, make sure you allow GRE frames if you wish to set those up, and make sure you do this pipex enable flag as well. And then from here, go ahead and reboot. And then on the Windows client, this is what we'll set up. So 192.168.1.133. You can enable anything that you may want here. We're using L2TP. This right here is where you specify your pre-shared secret. It will be blatantly obvious if you need to use it. And then, of course, when I hit connect, you can't see it, but a dialog will come up and we will be connected just as easily as that. We can view the details and you can see that we do have an address and that DNS server propagated right through. This does not by default use multi-link PPP framing unless you ask for it, but do be mindful that NPPPD does have questionable support for multi-link framing, which is to say it really doesn't. And that's basically it. That's all you have to do. Now, that's great and all, but I understand that a lot of people really like to do this on Windows too. So I think that I should provide a demonstration of how you might configure a dial-in concentrator on Windows. So in order to do that, you will use routing and remote access. So after you've installed RRAS, you will want to expand these here, network interfaces. This is where you can, if you wish, declare other outbound interfaces for dial out. Remote access clients, this is where the users will be listed, and then ports. So you can see this supports SSTP, which is probably the worst you could use, PPTP, PPPoE outbound only, and then L2TP, two-way, and then, of course, IKEv2, which is basically the logical successor to this. It's literally just a different way of doing a negotiation. Come over here, do properties, and from here you can configure, and that's, I think, relatively simple. If you do properties here on the host, then this is where you can specify your IPsec pre-shared key. Okay? So this is where you enable IPv4 routing, IPv6 routing, PPP right there. This allows many other useful things as well. And then you may wish to enable logging. However, you will probably want to properly configure your IPsec policies. So if you come over here and click Properties, come over here to IPsec Settings, click Customize, you can then change the IPsec parameters that are used. Because by default, it only really wants to use like 3 des, and like that's basically it. And oftentimes, there's a very important thing with Linux that we're going to look at in a second. Oftentimes, you probably won't have 3 des support, so it behooves you to ensure that you have it. So here's what I allowed. So I allowed AES 128 with the SHA-1, 3 des, SHA-1. These are the 2 defaults. These aren't very good. However, everyone nowadays uses SHA-256 with AES 256, so on and so forth, and then just throw in some more for good measures. Okay? For data protection quick mode, these are more or less something you can leave as default. These will be supported on pretty much any IPsec implementation out there. And authentication method default just means your bog standard pre-shared secret. It's the way to go. You can use Kerberos, but let's be real. If you're doing Kerberos for IPsec authorization, this video is not for you. You know way more than I do about this. Now, with that being said, you can also control who is even allowed to open IPsec tunnels, but do be mindful. If I come over here to inbound rules and I attempt to locate the routing and remote access rules, let's see, RRAS L2TP in, this right here, somewhere deep in this, will allow you to specify that you require IPsec for this. I do not believe it is actually in these dialogues, but by default, Windows is really going to want an IPsec rule here. So do be mindful of that. And also, you should probably already have known this, but the more recent version of Windows that you can use for this, the better. Because this old version of Server 2008 R2 does not actually support the hardware AES crypto acceleration functions in the CPU that this is running on. As such, the performance is somewhat questionable. So do be very mindful of that, okay? It matters a pretty big deal how fast you can run AES and 3DS encryption. So the more hardware you can use, the better. And with that being said, I'll go ahead and turn it back to what we were viewing before to go ahead and wrap up this video. And so with that, I'm going to sign it here. Everyone, hope you have a happy new year, and hopefully this video was informative. Goodbye.